here, and he's going to talk about topics in quantum entropy and entanglement.
All right. Well, thank you for the invitation. It's lovely to be here. I want to talk about two recent papers, both of which are on the web. Let me see if I can figure out how to use this thing. Nope, don't want that. Yeah, so one is work with Eric Carlin. That's the first thing I will talk about. And that already appeared, turns out, in Letters in Mathematical Physics. And the second, which has not yet appeared, but it's also on the archive, is with Rupert Frank, who lectured here a couple of weeks ago, but not on this topic. And let's go to the next page now. Let's see. How does this work? Okay. It's hard to read this. So first of all, I apologize for the fact that this talk is not about the topic of the program, but it could be interesting. And what I have here is some remarks from Schrödinger, who was perhaps the first to talk about entanglement as a concept. And what he wrote was the notion of entanglement, well, he didn't write this, but the notion of entanglement goes back to 1935 and was introduced under that name by Schrödinger in two papers. One was published in English in the Proceedings of the Cambridge Philosophical Society, so I guess that's appropriate because we're in Cambridge. And another was published in the Naturwissenschaften. And the latter paper, of course, I think maybe you haven't read it, but it's the paper with the cat paradox. I think everybody knows Schrödinger's cat. And both of these papers were written in response to the line of debate that was opened up in the paper of Einstein, the famous paper, ultra-famous paper of Einstein, Rosen, and Podolsky. And now here's a quote from Schrödinger, who says that entanglement, which he introduced, is not one, but the characteristic trait of quantum mechanics. So from his perspective, this was much more, and I have to say he was prescient in this. The most striking thing was not interference and wave-like nature of particles and stuff. He could live with that. But what he could not live with was this entanglement. It was the characteristic trait of quantum mechanics, and the one that enforces its entire line of departure from classical lines of thought. So this is the thing for which there's no classical analog. For waves, there is a classical analog. We can, I mean, the fact that particles are sometimes waves and sometimes particles, well, that's a little bit unusual, but at least we know what waves and particles are. But entanglement is something we don't know about. So what is this trait? This trait is that two physical systems that are brought into temporary interaction and then completely separated, meaning you could have one here and one on the moon, can no longer be described, even after the interaction is utterly ceased, by individual wave functions for each of the two systems. And that is, you cannot treat them as independent, however far apart they might be. And he wrote, by their interaction, the two representatives, or functions, that started out as two independent functions, have become entangled. And then you can't get rid of this entanglement. Now, the quantitative theory of entanglement as a mathematical theory has begun to be developed surprisingly recently. I mean, up to now, nobody sort of really took this seriously as being an important physical thing, but now people are regarding it as very physical and at the foundation of quantum computation, if we ever have quantum computation. So quantum information theory is based on that. Quantum communication and cryptography are also based on that. So it's important in the sense that it's at least intellectually important. Whether it becomes physically important or not remains to be seen. Okay, next page. Now, this lecture is intended to be a little bit pedagogical. So let me spend a little time mentioning things that some people know very well and other people have never heard of, and I hope those who know it won't mind. But so I call this some facts from the last millennium. And I begin with the definition of a density matrix. What is that? That's an operator rho on a Hilbert space H. And any such thing provided, first of all, it's trace class and has trace 1. And second, that it's positive semi-definite. Now, given that, this entropy makes sense because, of course, it's bounded by 1. If its trace is 1, its spectrum is bounded by 1, so log rho is negative. So this object is certainly positive, whatever it is. It might be plus infinity, but it is well defined. And it's a concave function of rho. That's a little theorem as an operator concave function of rho. So that's the quantum entropy of a density matrix. Of course, classically, in classical information theory or whatever, dynamical systems, rho is not a matrix, it's or an operator, it's a function on some measure space. In that case, log rho as a function can be arbitrarily positive. It's not bounded by 1, so log rho can be arbitrarily positive, so this gadget can be quite negative, and in fact often is quite negative, quite contrary sorry, to the quantum case. Now, things start to heat up when you consider the tensor product of two Hilbert spaces, H1 and H2, and suppose we have a density matrix on the tensor product. So in that way, in that case, we can define a density matrix, which here I'm calling rho 1, on H1 itself, simply by taking the partial trace on H2. Now, if it's, whoops, wasn't prepared for that. What is the partial trace? Well, you take any vector in H1, you tensor it with something in H2, and let that something be part of a basis, an orthonormal basis in H2. You compute the inner product of rho 1, 2 on this simple tensor product, and then sum over the basis in the second space, and that gives you, it turns out, an operator in the first space, and that operator is independent of what you took to be the orthonormal basis. In the second space, that's a little theorem, but it's no big deal. So this is perfectly well defined. And in the same way, you can define the rho 2 on the second space, and now we've got three operators, rho 1, 2, rho 1, and rho 2 on the respective spaces, and so we have three different entropies defined by this formula where the trace here is on the appropriate space. Now, the first thing that requires a little thought is the subadditivity of entropy. That is to say, whatever you do, the entropy on the combined space is always less than or equal to the sum of the entropies. So given rho 1, 2, we now have three numbers, and they satisfy this inequality always. And you get an equality if and only if rho 1, 2 was a simple tensor product on the two spaces. Otherwise, it's an inequality. So that's one of those things which is trivially true in classical probability theory. That is to say, when rho is a function, it's very easy to prove this. It's just a simple exercise with Jensen's inequality. Very simple. Well, you sort of prove it the same way in quantum mechanics. This is not a heavy-duty theorem. It's easy to prove. I don't remember who first proved it, but there it is. It's one of those things that carries over. Now, if we say that rho 1, 2 is pure, I didn't actually write it down. That simply means that as a state it's pure. That means to say rho 1, 2 is just given by, it's rank 1. So it's a rank 1. It's just a vector, so to speak, on H1, 2. So in that case, if it's pure, then it's relatively easy to prove that although the dimensions of the two spaces might be different, S1 is equal to S2, always. Now, it's, again, not difficult to see. In fact, you can do it by using the eigenfunction expansion of rho 1, 2, that given rho 1, 2, which is over here, which is not necessarily pure, I can find a third space, which I'll call H3, and a pure rho 1, 2, 3 on H3, that is to say rank 1 operate on this tensor product, so that when I take the partial trace over 3, I get rho 1, 2. So any rho 1, 2, however complicated, pure or not, can be thought of as the partial trace over some other space of a pure state on this other, the triple product. That's a simple exercise. How do you do it? Well, you simply use the eigenfunction expansion of rho 1, 2. So rho 1, 2 is a sum of rank 1 operators, and you use the sum, the index of the sum, as the third space. It's almost a tautology. But this tautology is it turns out to be extremely useful. Extremely, I mean, it sounds simple. It is simple, but you can get a lot out of it. So since this guy is pure, I have now the rho 1 by taking the trace over 2 and 3, which is the same thing as taking the trace over 2 of rho 1, 2. But I also have S2, 3. If I take the trace over 1, I have a new gadget, which I did not have before. I have this rho 2, 3 and a corresponding S2, 3. And because of what I set up here, because this guy is pure, these two things have to be equal. So what? Well, now I can do the following. I write S1, 2, since what I just said can be equal, using this representation or this purification or whatever you call it, this will become an S3, this will become an S2, 3, and this will become an S2. Putting this on the other side, I finally conclude that S2, 3, which I got from this guy, S2, 3 is bigger than S3 minus S2. Or, doing it the other way around, I get that it's bigger than S2 minus S3, so it's bigger than the absolute value of the difference. Now you can say, well, but that may be true, but who cares? Because this S2, 3 is just a special thing that I concocted. But it turns out you can play this record backwards. And by purifying this again, you get back to the original inequality, which was that. So the necessary and sufficient condition for this is this. I've just changed the indices. The indices shouldn't bother you. So given any two Hilbert spaces and a density matrix on it, the entropy, the total entropy, is on the one hand less than or equal to the sum. That's the subadditivity, just with different indices. It's less than or equal to the sum and bigger than or equal to the difference, and that's a kind of triangle inequality if you want. So we got this very interesting triangle inequality, this one, over here, which of course is also true classically. I mean, the probability theory. We got this interesting thing by doing almost nothing. But it's very important. Why is it very important? Because it says that an entropy of a combined system is, of course, sorry, it doesn't say that. Start the sentence again. In the classical case, where rho is just a function, one has always the fact that S1, 2 is bigger than or equal to both S1 and S2. That's very easy. So in other words, the entropy of this room is bigger than the entropy of any individual person. This fails in quantum mechanics. This statement here is false. I mean, as a theorem. This is false. It might be bigger, but in general, it's not. So one of the essential features of quantum mechanics is that the entropy of a big system can be smaller in quantum mechanics, can be smaller than the entropy of a subsystem. That is, you start with a rho 1, 2, it has an entropy which could be 0, because if rho 1, 2 is pure, then its entropy is 0, because the sum of the eigenvalues are then 1 and the rest are 0. So when you plug it into this formula, you get 0. So S12 can be 0, S1 and S2 can both be positive. So this triangle inequality here, this one, says that the residue of this classical inequality for functions, which fails in quantum mechanics, that the best you can do is this statement that the entropy of the combined system is bigger than or equal to the difference. That's all that's left of this statement. And therefore it's important, because I mean, it's the only thing you have to guide you. So this can be false. And I repeat, just because we're going to see this again, that the quantity S12 minus S1, which will be called a conditional entropy, can be negative in quantum mechanics. That's a sign of quantum mechanics. Okay. So now some more ancient facts from the last millennium. Well, the next sort of interesting fact is what is called strong subadditivity, which was proved by Ruska and myself, is the following. If I have a density matrix on 3 spaces, and if you want, let's see, there's no chalk. Okay, I'll make a little diagram. Think of this picture, sort of a Venn diagram. Call this 2, call this 1, and call this 3. So this part is 1, 2. This part is 2, 3. So if you have a state or density matrix on the tensor product of 3 Hilbert spaces, the entropy of the whole thing, which is that, put this on the other side if you like, plus the entropy of the intersection, which is this thing in the middle, is less than or equal to the entropy of the left side plus the entropy of the right side. So I can write it this way. S123 minus S2 is less than S12 minus S2. I can also write it this way, which is a little bit more pictorial, but it's the same thing. It's the question how you interpret it. And what this says, looked at this way, it says the difference in entropy. Remember, this could be negative, because a smaller system could have a larger entropy than a bigger system. This could be negative, and that could be negative. But this guy is more negative than that if they're negative. That is to say, adding a third space reduces the difference in the entropies. Whoops. Who designed this? Okay, now this theorem takes a little while to prove. It's not so easy. By now, there are many proofs, different kinds of proofs from different perspectives. But it turns out to play an essential role, and it will play a role here. Now let me use this purification trick again. I will regard rho 1, 2, 3 as coming from a rho 1, 2, 3, 4 that's pure by taking the trace over 4. I can do that. And this combination turns into that combination. So it says now if I have 3 spaces, which here I'm calling 1, 2, and 4, if I take the sum of the entropies, in this case 4 and 2, but with the 1 stuck on, and compare it without the 1 stuck on, then the entropy is bigger. It's also true classically. Now, so this statement is equivalent to that statement. These are 2 equivalent statements which you get by purification. So I will come back to that in just a minute. But before I do that, let me recall one other important fact from the last millennium, which is this, the Golden-Thompson inequality for matrices, for self-adjoint operators or matrices, which says the following. If I take two operators A and B, which are positive, and take the sum of the logarithms and take the exponential of that, then, and look at the trace, that is the sum of the eigenvalues, and compare that to what I would get if I just said this is A times B, using a naive formula for the exponential. E to the log is the function. Well, this is positive. Why? Because I can put in, since A is positive, or at least not negative, I can put A to the 1/2 here and A to the 1/2 there, in which case this becomes positive. So this whole object is positive. And in fact, it's bigger than the left-hand guy. So that's a very famous and ancient inequality due to Golden and Thompson, and it's one of the key ingredients in quantum statistical mechanics. And it's the theorem that enables you to prove that the classical, or rather, excuse me, the semi-classical approximation to a quantum mechanical partition function or quantum mechanical free energy of a quantum mechanical system is less than or equal to the classical entropy, a classical free energy. Because if you take A to be the Laplacian, or rather log A to be the Laplacian and log B to be a potential, then the left side is e to the minus the free energy, whereas the right side turns out to just to be the semi-classical free energy. So you get that important fact from this inequality. Now, the reason I'm mentioning this, and it will appear later, is the proof of this thing up here, the original proof, used in an essential way. It was based on the following generalization of the Golden-Thompson inequality. So there's this ancient Golden-Thompson, and here's the new version. It's the triple Golden-Thompson inequality. And this takes a long time to prove. This one is easy to prove. This is not. If I take e to the log A plus log B, excuse me, minus log C, all these are positive, then it would be nice if I could say that this gadget, in analogy with this inequality, is less than or equal to A, C inverse B. Trace of it. Well, it's not true. In fact, not only is it not true, but the left-hand side is not necessarily real, even. All right. However, what is true, all right. What is true is the following, that if I take A, the inverse of C plus T, T is we're going to integrate over T, or T times the identity, B 1 over C plus T, and integrate that, that one can easily see is real and positive, and it's bigger than that. So this inequality here is the generalization of that. Notice that if B and C commute, I can pull the B over, and 1 divided by C plus T squared is just 1 over C, so I obtain this thing, which now in this case is real and positive because B and C commute. So in that case, you get what you expect, but now if B and C don't commute, you have this essential inequality. Okay. So now I come to the new result. Remember, just to go back a second, remember we had this, which way am I going now? Yeah. We had this thing, if you recall, which was equivalent to strong subadditivity. Now I'm going to take the same kind of inequality, but with S2 and S1, and just add the two together. All right? So what do I get? I get something, well, S12 plus S14 plus S24, but there's a 2 here, is bigger than S1 plus 2S2 plus S4, which drives you to sleep. However, something interesting is going to come out of that. I got this practically for free. You recall, I just used this purification trick. Now you purify this thing. Again, as you find we have 3 spaces here. We find the 4th one that's pure. And use the fact that the entropy of partial entropes of a pure state, the 2 partial entropies are equal. You end up with this from that. And look what we have. Following interesting fact, that this quantity, which is positive by strong subadditivity, which is where we started, this quantity with a half is bigger than S1 minus S12. Now 3 here plays a special role, but I could put a 2 here by symmetry. So it's also bigger than S2 minus S12. So you say, so what? Well, recall that strong subadditivity said that this quantity was positive and that was the end of the story. Now we find that the right side, this thing, which is so-called minus the conditional entropy of 1 and 2, never mind what you call it, it's all, I'm sorry, classically, this is always negative. This guy is bigger than that. But in quantum mechanics, this thing could be negative, as I said before. So we reach the conclusion that when quantum mechanics is manifest, that is, when this quantity is positive, which is the sort of quantum mechanical regime, then there's a lower bound on the strong subadditivity quantity. Here it is. Now you say, well, so what? What good is that? Well, now we come to entanglement. Because you'll notice there's this little symbol here, which I have to explain. But this quantity, which I will explain, is defined this way. It's defined to be equal to this in a certain sense, which I will explain. And what we have here then is a lower bound to this entanglement entropy, which is what this is going to be, in the case that we're in the quantum mechanical regime. Okay. So what is this ESQ? Well, SQ stands for squashed. I didn't make that up, but that's what it is. And it was invented by 2 groups. One was Tucci, and a year later, Cristandal and Vinta. The Tucci paper is kind of obscure. He didn't do anything with it. He defined it, and that's the end of it. But Cristandal and Vinta sort of carried the ball and tried to make something out of this. They used this quantity to define a notion of entanglement. And here is the notion that they said. So you're given row 1, 2. You're given 2 systems, 1 and 2. That is, the Hilbert space is the tensor product of these 2 Hilbert spaces, corresponding to 2 degrees of freedom. Those 2 degrees of freedom can be 2 particles, or 1 particle with 2 degrees of freedom, like space and spin, or anyway, 2 Hilbert spaces. And I wanted to, and I've given a row on this tensor product, that is a state on this tensor product. And I wanted to find how entangled 1 and 2 are. The simplest case is when 1 and 2, the row 1, 2 is just a simple tensor product, but that's not the typical case. I wanted to find the entanglement. And what these guys came up with is the following. You take this quantity, which is positive by strong subadditivity, for an arbitrary 3rd Hilbert space. Now, they're not telling you what the dimension of the 3rd space is, or should be. In fact, there's no known bound on this, on the required dimension of H3. Anyway, you take this quantity, you make it as small as you can over all possible Hilbert spaces H3 and over all possible density matrices on the triple tensor product. Now, this is not a pure state anymore, the row 1, 2, 3. That's not required. So you do the best you can to make this as small as possible, and you call this the entanglement, the squashed entanglement. of 1 and 2. Now, I will, the word squashed refers somehow to the idea that this definition, there are many definitions on the market as to what entanglement could be. This is one of them. The claim here is that this has taken out, so to speak, as much of the classical, that is, classical component of the definition as possible. So what you're left with is only the pure intrinsic quantum mechanical entanglement. That's what's being said. But anyway, here's a definition. It's a mathematical definition. We have to take the infimum of this thing over all possible 3's. And the trouble with this definition is it's not so easy to compute. In fact, as I said, there's no known bound on the required dimension of H3. We don't even know that much. And what this inequality here gives you is a computable lower bound in the case that S1 is bigger than S12. It's computable. Why? Because it's part of the input data. What you're given, what the input is, the rho 1, 2. That's what you're told. And so this is, you can compute this right away. You don't have to introduce any third Hilbert space. Now, Cristano and Winder managed to prove this also, except they did it in the sense of taking the mean of the two. Remember here, oops, sorry, I went in the wrong direction. Remember I said you could just as well put an S2 over there as an S1, so you can take the bigger of the two. In other words, our bound, where you take the max of those two things, is of course better than taking the average of the two. That's much is clear. And when I gave this talk some months ago, or a month ago, in Munich, I was told that, well, that Cristano and Winder actually could prove this as well, but they didn't do it. I can't explain this. I mean, I have, whoops, suddenly died. Did I do something? Oh, no, there it is back. What happened? Oh. I don't know if that's true. We haven't had time to check it out. But in any case, the proof of this, of Cristano and Winder, is very long and complicated and uses two very deep theorems in information theory. So whereas the proof that I just told you just follows directly, almost directly, from strong subadditivity and this little trick of purification. Now, to make this a little bit clearer, we can note that there are states rho 1, 2 on the tensor product for which this difference is positive, so is S2 positive, and S1 and S12 can have arbitrary values greater than or equal to 0. Therefore, what can happen is that this quantity can be greater than or equal to 0 very easily, whereas this quantity, the average, can be arbitrarily negative. You can invent examples. So this really, the second one really is a lot better than the first one. Okay, so that's our contribution to entanglement. Not quite. Here's some remarks about it. The inequality is sharp. That is to say, it's false with any constant smaller than half. There is another definition of entanglement. Here's another. I said there were many on the market. Here's another one. It's called entanglement deformation, which is given in the following way. You split up rho 1, 2 into a sum of density matrices with positive coefficients. You do this as well as you can. You take the one entropy of the trace over 2 of these little pieces and you add them up. And you try to make that as small as you can. Now, by concavity of entropy, we can assume that the omega j's are rank 1, that is, they're pure. And from that it follows that S1 equals S2, as I said before. And so, although this definition looks unsymmetric between 1 and 2, it is in fact symmetric. Now, this entanglement of formation, which is older than the squashed entanglement, satisfies the same minimization principle as this guy, namely in terms of these differences. This is the definition, but you can convert it into the previous definition, but with a restriction on the allowed row 1, 2, 3, and therefore the entanglement entropy, namely this one, is bigger than the other guy. And we have a lower bound on this one, so we also have a lower bound on that one. Now you say, so what? Except the interesting fact is that the lower bound on this one, which we obtain, is also sharp. That is, the lower bound on this, given by our theorem, turns out to be a sharp lower bound to that one as well. So that's the remark. Okay, so that's the end of the first part about quantum entanglement. And I go on to the second part, but maybe somebody has a question or criticism or, yeah, oh, sorry.
Your bound, can't you get a better bound just by putting any CP map on?
Sorry, by what?
Can't you get a better bound just by applying any CP map to either system 1 or 2? Because your bound is in some sense, almost the distillable entanglement, but you can
A better bound on the entropy of formation?
on the squashed entanglement,
On the,
just by applying a CP map to either system 1 or 2. Like if I maximize this quantity by applying some CP map to S1.
I wouldn't know how to do that. I'm not saying you're wrong, but
Well,
if it were that simple, it would have been done by now.
Well, isn't it just the distillable entanglement? I mean, it's in some sense you're bounding it. You're saying it's larger than some quantity, which looks a bit like a distillable entanglement.
Mm-hmm. But it's
So the one-way distillable entanglement is just increasing that quantity by applying a CP map. I'm just wondering if you can get a better bound by just applying a CP map to
Well, I don't know how to answer your question, except that if it were like that, it would have been done a long time ago. And the only bound that I know in the literature is this Christandl-Vintner one. So something is not right. That's all I can say.
Excuse me, could you give an idea how can it be that S1 minus S12 is positive if, say, H1 and H2 are two-dimensional spaces?
Yeah, right.
So how does it look, this matrix, rho in this case, for which this hold S1 minus S12 positive?
Oh,
Yes, just examples. You claim that it happens, but
it can happen,
you
yes. And
give some
I'm
examples?
not ready to answer that question either.
Huh?
I don't know.
Okay, so it should be some matrix 4 by 4. Okay.
Yes, and I don't, it can happen. That's all I can tell you. Okay, now let's see the fact. Okay. All right, now this is the work with Rupert Frank, the other thing, also about entanglement. Although here we're talking more about measurement. So again, we have a density matrix and an orthonormal basis of a Hilbert space. And we can define the expectation value of the density matrix in this orthonormal basis. So let's call that Pj. So the A's you should think of as a measurement of rho. So this number P is it's the measurement of rho in that state. And we can define an entropy just by summing P log P. And the entropy of A defined in this way, it's not the entropy of rho, it's the entropy, we call this the entropy of A because we always think of rho as being fixed. This can be quite small even if the entropy of rho is large. And in fact, in the continuous case, I'll mention that in a minute down here, it can even be negative. Now, Maassen and Uffing, in a very famous paper, I forgot how far back this goes, in the 70s, no, even before that, found an uncertainty principle. Namely, if you take another basis and you look at the entropies, the sum that you get using the A basis or the B basis, this is bounded below by a quantity, a positive quantity, which is defined as the sup of the overlap between the A basis and the B basis. And so that was very famous, and you can generalize this to continuous basis, namely you can use delta functions and plane waves as the two bases in L2 of R. So here you have the density matrix rho that we started with, having elements in the as points in L2 in R, and here's the Fourier transform of rho. By that I mean the transform with respect to the first variable and the transform with respect to the second variable. You look at it on the diagonal, you look at this on the diagonal, and you multiply by the logarithm. That's what this is saying up here. And the sum of those two classical entropies of rho, defined in this way, one in X space, so to speak, and one in Fourier space, are positive. That's the contribution of Maassen and Uffing. But what you should notice is that each of these things, this one as well as that one, can be arbitrarily negative. Arbitrarily negative. Nevertheless, the sum is always positive. So remember, I mentioned this already, that in classical statistical mechanics, for continuous systems, the entropy can be, and often is, negative. Here with the measure dx on R. But although that is true, the sum in Fourier space and the entropy in X space is always positive. Now, what Rupert, Frank, and I managed to do is use some ideas of Roumain, recent ideas, and what we can prove is that the sum of these two things is not only positive, but it's bigger than the entropy of rho. Now remember that rho is an operator on some Hilbert space, so the entropy of rho is necessarily positive. And in fact, you can generalize this to any two bases with two measures on L2 of x, two Hilbert spaces, L2 spaces, x and measure mu, y and measure nu. And if u is a unitary connecting the two with an integral kernel uxy, that's bounded from L1 to L infinity, you can prove that this sum of these two gadgets, which still makes sense, is bigger than the entropy of rho, minus twice the logarithm of the norm of u as a map from L1 to L infinity. Now I'm calling this the Fourier transform. What this thing really is the unitary transform, which we talked about here, the unitary transform of rho. So I'm calling that the Fourier transform, but that's the analog of the Fourier transform. So these two quantities can each be arbitrarily negative, but the sum is positive. It's bounded by that plus that. Now in the case of the real Fourier transform, this is just one, so we don't learn anything. We cannot improve beyond S of rho, but in other examples, it can be different from one. For example, x can just be the integers, and y is the interval minus pi to pi, which is the Brillouin zone. Whoops, I left out an L. So the x integral here is a sum, and the y integral is continuous. That's an example. And this thing is somehow reminiscent of strong subadditivity. It's not, I mean, of just, well, yes, it's reminiscent of strong subadditivity, but that's a poetic fetch. It's not really strong subadditivity at all, but it's somehow reminiscent of it. And Roumain extended this to POVMs, positive operator valued maps, measures, but let me not go into that. But it's essentially what I wrote down. Now the proof of this theorem is very easy. One is it uses the classical Golden-Thompson inequality, which I talked about before, and the other is the Gibbs variational principle, also known as the Piles-Bogoliubov inequality for matrices, for positive definite matrices. No, here it doesn't have to be. That the trace of rho h plus the trace of, yes, here it has to be positive. The trace of rho log rho is bigger than minus the log of the trace e to the minus h for any h. So this is the Gibbs variational principle, which is equivalent to the Piles-Bogoliubov inequality. Now, so far, what I said looks quantum mechanical, namely we have one density matrix rho on some L2 space, and there are two kinds of entropies that I can define. But now, but it's somehow not intrinsically quantum mechanical yet. It's just classical harmonic analysis, if you like. But now we turn to more serious matters which are truly quantum mechanical and really use strong subadditivity and the triple Golden-Thompson inequality that I mentioned before. So we want three Hilbert spaces this time, which I will denote by H1, H2, and H3 as before. So think of L2 spaces if you like. And here's a quotation from Schrödinger about all this, but since I'm running out of time, I won't read it. But he's saying that the measurement problem in quantum mechanics is impossible. And he says here, the best possible knowledge of a whole does not necessarily include the best possible knowledge of its parts, even though they may be entirely separated. So again, it's this entanglement problem. So the entanglement and the measurement problem, and I remind you that these expectation values are really measurements of the properties of rho. I'll make that more precise now. So I won't bother going through this. So what is a measurement? Well, it's a classical measurement. Now remember that we have a density matrix, the rho, which describes the state of a quantum mechanical system. But what we do in the laboratory is we make measurements with meters and things like that, and those are called, or we can call them, classical measurements. So what is it? Well, you have a bunch of operators. So think of the orthonormal basis as a kind of example of this. It isn't exactly the same thing, but it's very similar. So in this case, we have a bunch of operators, aj, not vectors, but operators, so that the sum of the a dagger a's is 1, and this defines a completely positive map by the Krauss representation. So the probability of the measurement j is then, by definition, the trace of aj rho aj dagger, or star. And I remind you what the conditional entropy is. It's this gadget, which classically is always positive, but quantum mechanically can be negative. And now I'm going to define the classical quantum conditional entropy. So classical refers to the fact that you look at these numbers, and quantum means you take the trace of rho log rho. Okay. All right, so what do? We take this rho, which lives on the tensor product of two spaces. The a's are measurements on the first space, so they're on H1. So we conjugate with the a and a star. We take the trace over 1 now, so this depends only on 2. And that gives some probabilities on 2, which add up to 1. And, or rather, density matrices on 2. And we take the trace of this times the log of the same thing, which is an entropy. And we call this the entropy of 1 relative to 2 with regard to the, depending on the measurement A, with this collection of operators AJ. And for convenience, we subtract S2 just to make things work out nice. Okay, now, so this is, of course, the remark here is that the sum is however, outside, not inside. So it's not the conditional entropy of this gadget. You see, the J sum here is not done in here. It's done over here. Okay, so now we need some theorems. Now these theorems appeared in the literature in one form or another with very long and complicated proofs. And this paper that I'm referring to here, everything is done in a few lines. Basically, that's the point. And what the key to doing this is this triple Golden-Thomson inequality, which let me go all the way back just to remind you what it is. It's this thing. If you use this appropriately, everything sort of falls into place very easily. Whoops. Okay. So the first theorem says you take two different measurements. You take the A measurement and you take the B measurement. The rho, the density on the combined space, is the same in both cases. In one case we measure the A's, in one case we measure the B's. And how are these related? So we're really comparing two kinds of entropies. And the statement is it's bigger than or equal to the conditional entropy, and defined up here, which I remind you could be negative, minus, rather plus, if you like, a positive number. And what is this number? It's the sup over J's and K's of the A's times B's squared. It's a sort of an L2 norm of AB. So it's like very similar to the inequality. Where was it? Here, yeah. The inequality, the ancient inequality of Masson and Uffing. Okay. All right. Good. So that's the theorem. So if rho is a tensor product, then this just becomes the Masson-Uffing inequality. Okay, so this theorem that I just mentioned is difficult because it brings out the terrors of entanglement. It was conjectured in 2009 by Rennes and Boileau, who realized that the strong subadditivity theorem was somehow crucial to it, but they couldn't get beyond that, really. Then Bertha and others proved this special rank 1 case, where all the A's and all the B's are just orthonormal rank 1 projectors. So this takes us back to the vector case, which was the Masson-Uffing case. So in that case, they could prove this statement about two Hilbert spaces, or two measurements, but only in the rank 1 case. Then after that, Coles and Thomas Michel and Renner eliminated some of the rank 1 conditions, but not all of them. All these proofs were very long. The original Renner proof was, I don't know, 10 pages in Nature, and really quite complicated. So it turns out that the theorem which I just mentioned can be proved in a few lines by merely adapting the original proof of strong subadditivity, which used as a key ingredient, as the main stay of the theorem, of the proof, the triple Golden-Thomson inequality. Now there are a few more theorems. You can compare the three spaces with the second space here. So first of all, we have two different measurements, and here we have space number 2 and space number 3. Oh, sorry, the second space here and the second space here can be different, which I'm calling 2 and 3. So there are really 3 spaces involved. And again, you get the same kind of inequality, but now you get this appears against. And let me not go into this. This is sort of in between the two theorems, but it turns out you prove this before you prove that, and but it's of less interest. But this one is one where people worked really hard for a long time. Now you can do the same thing for Fourier transforms for the continuous version, and here I've sort of illustrated it. So again, you take a density matrix on two spaces, you compute the matrix element in one basis in L2, and you compute it in another basis in L2. But the basis here refers to the first space. Then you take, after you've done that, you then have a function on 2, and then you, rather an operator on 2, and you then take the trace on 2. So it's the operators don't commute, and that's the source of all the problems. So this is very much more difficult than the previous Mason-Urphy. Now I know I've bored you to death, so thanks for listening anyway.
Questions or remarks?
How would the quantum thermodynamics looks like?
How
I
would
mean,
what?
you have entropy, additivity in classical thermodynamics
Yeah.
of the entropy.
Mm-hmm.
But here you don't have this. So
What is it you don't have? Sorry.
additivity of the
For
of the
disjoint
entropy.
systems.
Sorry?
Additivity of entropy for disjoint systems. That's what you're talking about, right?
I
Classically.
didn't say they are disjoint. I mean, they can be. They have some interface. But,
Yeah,
in classical physics, you have entropy.
You still have that here. That's called the existence of the thermodynamic limit. And that's true in the thermodynamic limit for quantum systems.
Ah, okay.
That's
so
true.
if it's
That's a
large
theorem.
enough,
That's
you
large
don't
enough.
have this effect.
That's right.
Okay, thank you.
That's right. But these things are for small finite systems. They're for, finitely many degrees of freedom. In fact, it refers to a code or whatever, to a message or a way of a channel, more precisely. So it's quite a different story. But what you say is true in the thermodynamic limit. And people went to a lot of trouble to prove that in the 50s and 60s.
So we don't know anything. We don't know hardly anything about three measurement inequalities, uncertainty principles. Can you use those tools to prove an uncertainty principle for three measurements, or does it only work for two
No,
measurements?
for two.
And you can't extend it to three.
But you can have different ones. Remember, you have different twos, 1, 2, and 1, 3. I mean, in that sense. The inequalities that is that what you're talking about?
Yeah,
There are only two spaces, but two different.
I guess it's an uncertainty principle for two measurements, like say.
Yes, right.
position momentum. I was wondering, since we don't know anything about uncertainty principles for three measurements, whether
No, that's
one
right.
can extend it to that.
That's right. There's nothing I can say about that. But there is a third space in the sense that, let's go back here, over here, right, in the third space. I mean, this refers to a row 1, 2, 3. But it's only two measurements. So the only thing I could say is by taking this theorem and adding it to itself.
Other questions?
I don't know of anything in the literature that refers to three measurements, but maybe I'm wrong. Maybe there's some expert here who knows, but I don't know.
There isn't because we don't know, but that's why I was asking whether you
Oh,
could.
right.
whether you could extend it.
Oh, maybe you can do something.
If there's no more questions, thank you very much.
Okay.